Good morning, everybody. I apologize that I'm not able to give this talk live, but I'm on the road, and I also apologize that I'm really losing my voice. So I do hope that I will be able to speak throughout this recording. So what I want to talk about today is I want to highlight a couple of the findings of the Intergovernmental Panel on Climate Change, and I want to focus especially on what challenges for energy system modeling entail based on my reflections on the recent IPCC reports. Of course, most interesting will be after the Working 3 report is published, which Tony knows extremely well, but I'm afraid we have to wait a couple of more months for that. So first of all, we could summarize the recent IPCC report like this since the 1990s, that we are kind of saying the same thing. Perhaps the microphone wasn't on, it's very likely, but the word has changed very significantly just within the 3 decades since the IPCC has been trying to say kind of the same things. So because when we say already in this report that recent changes in the climate are widespread, rapid, intensifying, and unprecedented in thousands of years, and the thousands of years is probably a little bit of an understatement, or it's a compromised statement. Let me just show a couple of concrete points from the report where how much we have already rewound the geological clock of the Earth. For example, carbon dioxide concentrations have not been so high for at least 2 million years. The global average temperature has not been so high for at least 125,000 years. Ocean surface acidity has not been so high for 2 million years. Global surface temperature has not been sustained at 2.5 degrees higher than pre-industrial average for at least 3 million years. So that means that still within this century, very likely fairly soon, we are going to exceed the 2.5 degrees warming. Then we have already rewound the clock of the Earth geological clock by 3 million years. Unfortunately, IPCC also emphasizes in this latest report that there is no going back from some changes in the climate system. So even if we tomorrow don't emit a single molecule of carbon dioxide, we have already set some changes afoot, which we can't go back to. So these are, among others, the ocean temperature, which will keep increasing for hundreds, if not thousands of years. The same with the Greenland ice sheet, as well as the rising of the sea levels. And this particular report already details much more also the tipping points, so or the low likelihood, high impact outcomes and tipping points in which the climate system or part of the climate system goes into another state from which it's very difficult to return, or may take, if it can return, it may take at least thousands of years. So we are actually dangerously close to some of these tipping points. For example, we don't know exactly. We just hope that loss of the Greenland ice sheet will happen, will be set off between 2 and 3 degrees, and the threshold for the collapse of the West Antarctic ice sheet is also going to take place between 2 and 3 degrees. The abrupt collapse of the Atlantic meridional overturning circulation, which includes the Gulf Stream, we hope it's not going to take place this century. The report says that it's not likely that it's going to happen. Nevertheless, since our report was finished, a new Nature paper showed that perhaps we can already observe the signs of this instability, and that's what recent data suggests. So our confidence statement on this is less strong as before that paper. These include also forest dieback, Amazon dieback, and also the subsea and permafrost gas breath rates, which basically mean the methane, which is now trapped in these soils, in these areas, which can accelerate global warming. So this is not from the IPCC, this figure, but it shows very well that with the different scenarios, how many, when we are likely to cross which tipping points, thresholds with different scenarios. And it's very clear that that already fairly soon we are already setting off some of really dangerous climate processes. So the good news part is that, however, some changes could still be slowed, and many could still actually be stopped and fully reversed by limiting warming. However, what we also said, that unless there are immediate, rapid, and large-scale reductions in greenhouse gas emissions, limiting warming to 1.5 degrees will be beyond reach. So that means that already very likely towards already within a decade, we are going to most likely reach 1.5 degree global warming. And in all scenarios, basically, it's also likely that in the next 5 years, there will be individual years where we could already exceed it sooner, but on average, this will take about a decade. However, there is a very major difference between stabilizing the climate at this level and perhaps overshooting a little bit, but returning to this level, or going towards the worst scenarios where just within this century, we could reach potentially over 5 degrees of global warming. But here come the important findings, which have very important implications for all energy modeling. So what we knew before, but now this report phrases crystal clearly that limiting human-induced global warming to any specific level requires reaching at least net zero carbon dioxide emissions, and may require radical reductions in other greenhouse gases as well. This means that even if we let the 1.5 degree target go, even if we let the 2 degree target go, even if we let the 3 degree target go, even if we just want to stabilize finally at 10 degrees of global warming, which I'm not sure if humanity could survive, but basically, if we want to stabilize the climate at any level, if we want to keep it survivable, net zero carbon dioxide emissions is non-negotiable. It's a target that we just have to reach. So if we need to give up fossil fuels, and if we need to keep them in the ground, these are already thoughts that I'm adding until this, it was the report, and from here, these will be my reflections. If we need to do the energy transition anyway, then it's very important that basically it's our responsibility what the climate will be like for potentially for thousands of generations, because the point is that how soon we can get to this non-negotiable net zero target determines our future climate. So this is why a rapid decarbonization and the rapid energy transition is an even bigger responsibility than we thought before. And yes, many of the scenarios that I showed earlier in the figure do not reach and do not even get close to, or don't even start in the direction of net zero. So to the scenarios that I showed earlier, only 2 reach net zero within the century, and the third is at least reaches towards, but the other 2 will entail still a constant further warming, unless these also start to not only cut down the scenarios, but go down to net zero levels. So because the most recent report shows that we can still perhaps stay at 1.5 degrees, let's just look into a bit these futures in more detail. I know you're all aware of this, but I do want to emphasize some important conclusions from integrated assessment modeling, because because this is where the IPCC elaborations rely, especially Working Group 3's elaborations rely very heavily on integrated assessment models. It's really important that to understand that these are extremely important models, and we couldn't say all of this about how to link climate change to specific or energy transitions to specific warming levels without them. Nevertheless, it's really important to understand that they also have limitations, and this is where all your models that you're doing come in, and all your models become so important to help us understand the details and the conditions and the closer policy implications of aspects that IEMs are weaker at, or where their richness of details stop. So let's just look into these clouds of different scenarios. So yes, there are many scenarios that can reach there, and all of these are done with integrated assessment models. But as you can see, the vast majority basically all imply very severe negative emissions in the second half of the century for this reaching this temperature target. But even now, for reaching 2 degrees, they most rely very heavily on negative emissions. So let's just pick apart P4 based on our 1.5 degree report. And if we do that, we see that the vast majority of emissions in this part of the first half of the decade will come from fossil fuel related emissions. But that means, and we don't reduce that fast, but that means that in the second half of the century, we basically have to get to very severe amount of negative emissions already in 2050. So in the middle of the century, we would already have to get to something like close to 20 gigatons per year CO2 emission reduction. Remember the number 20, because I will show what these entail, for example, with BACs. Even other scenarios entail very significant, very large numbers of these negative emissions. One important problem is, and why we shall see that also in Glasgow, now lots of the youth will be on the streets, and why we understand better when we look at these scenarios, because basically what this means that we still keep continuing our lifestyles of today, while the next generations are going to have to pay very significant price for this, because negative emissions have no payback times. They can only pay back from the carbon price, and they're likely to be altogether rather expensive, especially if we have to do them at this particular scale. So yes, recently the scientific literature has raised a lot of worries about offsets and generally negative emissions, and criticizes reaching targets, net zero targets through offsets, as paying someone else to go on a diet for us if the doctor says we should go on a diet. For example, a recent EU report showed that only 2% of the projects which were aimed at reducing emissions elsewhere, and only 7% of potential CER supply have a high likelihood of ensuring that emission reductions are additional and are not overestimated. And also carbon storage on land as means to offset CO2 emissions from burning fossil fuels is scientifically flawed, said another paper. Also, there is a great concern that these just divert attention away from making own reductions. So, but perhaps the most important worry is that we will need negative emissions, even in the most ambitious mitigation scenarios. First, because there are industries or there are areas which are extremely difficult to decarbonize, or we don't even yet have the technologies, and we definitely won't have the technologies at scale and at affordable level until the middle of the century. Or even if we don't use negative emissions for neutralizing present-day emissions, we likely will have to touch these technologies for trying to limit, for example, the overshoot and come back from the overshoot to more bearable temperatures. However, the point is that there are limits to the scale of negative emissions, of carbon dioxide emissions, removals that we can do. For example, if let's just do a thought experiment. This is a paper that was that taking just 3.3 gigatons of carbon out of carbon dioxide through by the means of BECCS, bioenergy combined carbon capture and storage, which, for example, the IPCC scenarios used to rely very heavily on. This would entail over 3 times the word total harvested land for cereal production. This would require more than twice the word annual water use, present annual water use for agriculture. And we know that most of fresh water is now on the planet is used for agriculture. 20 times the US annual nutrient use, 106 times the word total coal-fired power plants capacity would be required to, therefore, these are very extremely high, as we not yet discuss the environmental risks, the impact on biodiversity, the risks of permanence, and many other concerns that emerge with many of these technologies. So basically, yes, and another point about this, that the recent IPCC report warned that, as we know, that CO2 when we emit, some parts stays in the atmosphere, but some other parts are absorbed by the ocean and land. Now, what the recent report warns, excuse me, that as we warm or as we go towards higher emission scenarios, only a lower and lower share of our emissions is taken up by the land and ocean sinks. So what this means is that if we emit the same amounts of carbon dioxide in a high emission scenario, so later, that actually entails much more warming than 1 ton of emitted carbon dioxide today. So that's also true for the reverse. That means that if we want to capture carbon dioxide and remove it from the atmosphere, actually from the same amount of atmospheric carbon dioxide concentration reduction in a high emission scenario, so later on, we will need to remove much more carbon dioxide than now to reach the same CO2 concentration decline. So that means that it's going to get harder and harder to actually reach any impact through removing carbon dioxide from the atmosphere. So as a result of this, and there are many other arguments, more and more scientists have been raising the alarm that the concept of net zero is a dangerous trap. This article in the conversation, which I recommend you to check out, was co-authored by many eminent climate scientists, among them by Bob Watson, who was one of the chairs of the IPCC. So as a result, which is important, why I said all of this, that we really need to try to go towards the scenarios where if you want to minimize risks, it's much safer to go towards the scenarios where there's the yellow is not present, even if the yellow doesn't come from BECCS, but direct air capture. But we understand now that direct air capture is likely to stay very expensive for a while, since you have to take very diluted, extremely diluted air. Just think about that. We have only 450 parts per 1 million part of air. We have to try to take that somehow, that carbon dioxide out and store it permanently. And taking this out, if you understand thermodynamics, so if something is so dilute, it will require a lot of energy input, whatever we do, and that will require very significant additional energy capacities, let alone other natural resources as well, and also huge machinery and much equipment, which already in themselves also entail a lot of embodied carbon dioxide. But even if we manage to do this all from renewables, just imagine, and that's also is a big challenge for energy modelers, that already decarbonizing the heating, the mobility sector, aviation sector, many of the industrial sectors. So there is a lot of very significant additions to our requirements for clean energy capacity, green energy capacity in a very short time frame. So adding also this enormous capacity, clean energy capacities, just for the sake of taking out CO2 from the air, would just increase our need for adding these amazing amounts of clean energy capacities, which poses further challenges to the feasibility of the energy transition, because this energy crisis that we are now in, although it's not yet a full-fledged crisis, but certainly an energy challenge that we are, energy supply challenge that we are facing now. This reminds us that we, even though solar energy has become the cheapest energy source in the last few years, we still, and there is so much investment going towards green areas, we still haven't been able to accelerate green energy supply additions sufficiently enough. And at present rates, it will take well over 100 years to reach our goals of a green energy transition. So to reach our decarbonization targets. So already our just supplying our present energy demands with clean energy will require very significant challenges for scaling our clean energy generation capacities up in time. So adding to that the needs for negative emissions would further challenge the system. So again, let's go back to this, and let's now focus then on the scenarios where we have very little, where we have a much more limited need for carbon dioxide removal. All scenarios have some, but where we have a more limited of these. So basically, these entail quite a large number of challenges that we still are ahead of us in terms of energy modeling. And among the reasons is that, as I mentioned, IAMs are indispensable tools, and they have been able to enlighten us with these very, very important policy messages and insight. However, they are much poorer on understanding the demand side opportunities, and all this work shows that we really need to focus on the demand side if we want to reach these ambitious targets without major negative emissions. There is no way around, and a very rapid change reduction in energy demand. And but however, we are still not very good at, especially IAMs, but also our models, which would be able to be coupled together to model behavior change, lifestyle choices, non-technological options, and sufficiency alternatives. And these projects that you are going to present in the next, and your effort that you will present in the next few days will fill a lot of these needs in, but these are really important, that these actually fertilize each other, are coupled, and in the end can be scaled up to enrich whole European understanding of energy solutions. Focusing also we always only focus on how do we produce the next kilojoule of energy or next megawatt hour of energy. No, in order to be able to bring down energy demand, we have to focus on how to deliver energy service demands better, and perhaps without actually having to go for energy, for example, through digital solutions. Also, we have not been very good at modeling complex systemic solutions. For example, net zero energy or energy positive buildings, retrofits, districts, and in general, modeling rich technological detail and sectoral interactions we have not been very good at so far, and this requires much more work. And as an example, for example, that we can do also with retrofit, this is basically the 21st century power plant. This is the TU Vienna. This building produces more energy than it consumes. But the trick to this was not only putting on a lot of PV, but the real trick behind this, and that's really important, is that let me show, because and earlier I said this was impossible, but because originally this building consumed about 800 kilowatt hours per square meter per year. Even advanced modern office building in Vienna consumes maybe 450. Nevertheless, we can only produce roughly 60 kilowatt hours per square meter per year for PV energy. Now, there is a huge discrepancy between the two, so one would think that net zero is not possible, but actually it has become possible. But the trick to this was this. You don't need to understand German, because the point is simply, this is a very diverse set of energy demands in these buildings, and as in many buildings, but we can actually very significantly reduce these. So with concerted efforts and detailed studies, for example, also in this building, they managed to reduce the energy demand by a factor of 10. And this is not only heating, but all kinds of different energy demands. But this required the optimization of 9,300 components. So that means, but it wasn't rocket science. This was students or just some engineers going around and thinking about these components. So that means that yes, we can significantly reduce present-day energy demand in buildings, and that's the trick to the energy transition, because if we do manage to reduce the energy demands very significantly, then we are much more flexible in our solutions. But this is very rarely modeled. There are very few energy models in Europe which really can reduce are able to do this complexity, that it's not about just changing one technology or one price signal or something, but we are talking about a very complex set of solutions, systemic approaches to solutions, and also how that this actually could be scaled up. And these are not expensive solutions, and the solutions are available everywhere, and these don't entail lifestyle changes. So this can be scaled up, but presently none of our energy models is really ready to show this to policymakers how to get there, and that these are feasible. So with the 56 kilowatt hour per square meter per year, this has been possible to convert this high-rise office building, which is usually, as we know, the highest energy demanding buildings, also as an energy positive buildings. And this was not a one-time case. For example, CEU's, my university's new campus, will be in Vienna in this beautiful Art Nouveau historic district. And we are, hopefully, it looks like we are also going to retrofit this to an energy positive district, and with the maximum protection of its historic heritage status. And actually our research on this has just received last week an Austrian state recognition. So yes, it is possible, and not only is it possible, but in fact what we showed that it's actually already cheaper at the first cost level, the retrofit, than regular retrofit, because you the very expensive part would be retrofitting, having to retrofit the building, the district heating system. So if we tend to forget that if large-scale infrastructure is expensive, already to build has a lot of embodied emissions and also expensive to maintain. So just two final points. I think what is also important to try to be able to model on a large scale European scale much better the embodied energy, for example, in infrastructure, for example, in buildings. We rarely model this, for example, some emission reductions through cement or steel. We rarely model it as a building design issue or an infrastructure or a mobility issue. We just treat it as a cement steel industry issue. But now we today do have the solutions for this. I will show you in a second. And also what is really important is how we report emissions actually in the end really influences and how we model and how we categorize in energy models the emissions really determine how we see the lens, how we see how policymakers see the energy transition. And this is just an example. Then we can already build skyscrapers from timber, bio-based materials, which here is a triple win because this is a passive house actually in Canada, so in a cold climate, but also it reduces substantially the emissions through avoiding concrete, so cement use, but also it captures carbon or stores the carbon of the wood for as long as the building stands. So at least removes that CO2 from the carbon cycle. Now, another challenge that this shows that, yes, of course, we may not have enough wood for all the European construction, industry. However, we also can use other materials. This is a beautiful house that actually uses straw, and straw construction, straw bale construction is more and more widespread in many European countries. So, but of course, there is a question how we have very limited biological productivity in Europe, and what's the best use of it for a most optimal climate future. And that's also certainly something that's very important for coupled energy models to answer. And here is what I want to show, that how we break down emissions very significantly determines how we see the energy the climate problem. So we can see it as an energy supply problem, or, for example, an architecture challenge. And this is from the 5th assessment report. So if the way how report our emissions basically right now show or present most our presently climate problem most as an energy supply problem, and buildings, for example, play a very little part. But if we allocate the emissions of the power plants, the energy sector, actually buildings get the largest share to this, and then suddenly buildings become the largest emitters, or the largest responsible sector for, or close to the largest, for climate change. So how policymakers see the climate problem is very much also an issue of reporting problem, and also then how we model and how we consider the different sectors. So what I want to conclude is that our future will be a sum of mitigation, adaptation, and the remaining suffering. We can't get out of this without any cost. So these we will entail costs anyway. Simply the point is what mix of the three our future will be like. So which mix of mitigation, adaptation, suffering is still now that we can determine. And in fact, we can choose the cost of mitigation. We can choose how we mitigate, still not for long. However, we have no choice in how we actually suffer. So really the future is in our hands now. The climate we experience in the future depends on our decisions now, and also what our remaining options for mitigation are really very largely determined by actions now. Thank you very much for your attention, and I wish you a very successful discussions in the remainder of this conference.